As the scientific understanding of aging grows more sophisticated, researchers are beginning to look beyond traditional metrics like blood pressure and cholesterol to uncover deeper, more precise indicators of health span. Among the most promising developments in this area is the identification of novel molecular markers that reflect the true biological age of our vascular system, one of the most critical predictors of overall longevity. Two such biomarkers gaining traction in aging and cardiovascular research are proadrenometalin, PAM, and bioactive adrenomegalin, BioADM. These molecules, once obscure, are now emerging as powerful indicators of vascular integrity and potential therapeutic targets for extending health span and preventing age-related decline. Vascular aging, marked by endothelial dysfunction, arterial stiffness, and chronic low-grade inflammation, is a major contributor to the diseases most associated with aging, including heart disease, stroke, kidney failure, and neurodegenerative conditions. What makes PAM and bioADM compelling is their close association with vascular function at the molecular level. Adrenomegalin is a peptide involved in maintaining vascular tone, protecting the endothelium, and regulating fluid balance. Its precursor, PAM, and its active form, bioADM, circulate in the bloodstream and increase in response to vascular stress and endothelial dysfunction. Elevated levels can reflect early signs of vascular compromise, even before symptoms of disease emerge. Recent studies have shown that higher levels of PAM and bioADM are linked to worse outcomes in a range of conditions, such as heart failure, sepsis, and renal disease. But they are now also being studied in the context of biological aging. Researchers have begun tracking these markers alongside chronological age and traditional risk factors to evaluate their ability to predict who is aging faster or slower at the vascular level. The results are striking. Individuals with lower levels of these biomarkers tend to show better vascular elasticity, lower systemic inflammation, and fewer signs of organ damage, regardless of their age on paper. What makes these markers particularly exciting in the context of longevity science is their responsiveness to lifestyle and environmental inputs. Like other aging clocks, such as DNA methylation-based clocks, PAM and bioADM can potentially be influenced by interventions such as diet, physical activity, stress reduction, and pharmacological therapies. For example, diets rich in omega-3 fatty acids, polyphenol, and anti-inflammatory compounds appear to reduce the burden of endothelial stress. Regular aerobic exercise promotes the release of nitric oxide and improves endothelial resilience, potentially lowering bioADM expression. In this sense, PAM and bioADM could serve not just as diagnostics, but as real-time gauges of how lifestyle choices impact biological aging. Therapeutically, interest is growing in how modulating the adrenomegalin system might help prevent or delay the progression of age-related vascular decline. Experimental treatments that influence ADM pathways are being explored for sepsis and heart failure, and some researchers believe similar strategies could be adapted to proactively protect the vasculature in older adults. Because these peptides play a central role in maintaining the integrity of blood vessel walls and regulating immune response, they could also become crucial in delaying or preventing the silent buildup of vascular damage that underlies many forms of chronic illness. Another promising direction is the integration of PAM and bioADM into personalized aging assessments. As wearable devices and digital health platforms become more advanced, the possibility of real-time biomarker tracking is not far off. In the future, a person's vascular age, reflected by levels of these molecules, could help guide individualized strategies for preventing cardiovascular disease or cognitive decline. Much like monitoring blood sugar or cholesterol today, assessing vascular biomarkers could become a standard component of proactive, precision longevity care. In long-lived populations such as those in Salento or Sardinia, there is indirect evidence that low levels of vascular stress may be a hallmark of their extended health spans. Though these communities are not yet widely tested for PAM or bioADM levels, their lifestyles, marked by high physical activity, low processed food intake, regular social engagement, and low chronic inflammation, align closely with the behaviors thought to favor vascular health and, by extension, lower expression of these molecular stress markers. The study of biomarkers like PAM and bioADM represents a paradigm shift in how we understand and potentially control aging. Instead of waiting for disease to manifest, science is moving toward earlier detection, finer-grained diagnostics, and personalized strategies aimed at maintaining optimal function for as long as possible. The vasculature, once seen as a passive network of blood vessels, is now recognized as a dynamic, modifiable system that reflects our overall biological vitality. In this evolving landscape, PAM and BioADM are not just numbers on a lab report. They are windows into the aging process itself, and possibly keys to unlocking longer, healthier lives.